Welcome back. So we are starting kind of our second new topic for grade 11 chemistry, and we're going to be talking about periodic trends. So this is something that we are going to revisit in grade 12 chemistry, so it's something that you're definitely going to need to know. Well, you might find them overwhelming at first. If you can understand periodic trends and how the periodic table is organized, I promise you it's going to make your life much easier, and it is going to make for far less memorizing down the road. So if you can understand how the periodic table works, how some of these trends work, you're going to understand the nature of chemical bonds so much better, which is really what this unit and what chemistry is about. So what we're going to start with is we are actually going to start with reviewing a trend that you've actually seen before, that I showed you in grade 9, and I showed you again in grade 10. So many observable trends in the chemical and physical properties of elements are observable on the periodic table. We are going to start reviewing the trend of reactivity. So remember, reactivity is just how reactive something is. So I want to take you back to grade 9 when we talked about alkali metals. And those of you that had me, we actually did the demo with alkali metals where I took the metal, I dropped it in water, and we actually went through this trend, not talking about periodic trends, but we went through this trend and we actually saw which metal was considered to be more reactive. So let's talk about reactivity. Reactivity has to do with group 1 elements. So one trend that you may be familiar with is reactivity. Reactivity is high in group 1, it's lower in the middle of the table, and it's high again in group 17. Low noble gases are considered to be the least reactive. So group 1, just a reminder, group 1 is those alkali metals. And remember that when we drop those alkali metals into water, they actually caught on fire. So we consider alkali metals to be very reactive. Halogens we studied are also very reactive. Alkali metals and halogens are reactive for a similar reason. They're only one valence electron away from being full. So alkali metals only need to lose one valence electron to be full. That's really easy to do. Halogens only need to gain one alkali metal to be full. That's really easy to do. Noble gases are totally unreactive, and that's because they're already full. They're not looking to gain or lose any electrons at all, so they don't react at all. So we've known that since grade 9. That's not too complicated. That's an example of a periodic trend. So we know, even if we don't know something's properties, even if it's a brand new element to us, we know if it falls in the alkali metal category, it's probably going to be reactive. So by understanding periodic trends, we can understand the properties of those elements. So I'm a very visual person, so let's go ahead and let's take a look at what this trend actually looks like visually. So we said that one of the most reactive parts of the periodic table are these alkali metals here. There's also another trend within here. We talked about this in grade 9, but I don't expect you to remember it. When we looked at our alkali metals, I actually showed you lithium, sodium, and potassium. We saw that lithium had a small reaction, sodium had a bigger reaction, potassium had an even bigger reaction. I couldn't show you rubidium because rubidium we don't have in the school, or cesium or francium. But essentially, not only are alkali metals the most reactive, alkali metals increase in reactivity as we go down each group. The reason that this happens is to do with where the electrons are. The electron in lithium is really, 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 really close to the middle. It's close to the nucleus. It's close to those positives. It's being held in there better. Whereas if we look at sodium, the valence electron is farther away from that positive core. It's not held in there as well. It's easier to lose. If we look at potassium, it's even further away from that positive core. It's even easier to pull off. Rubidium, cesium. So there are actually trends not just within groups, but there's also trends down groups. It's the exact same, but the opposite trend in nonmetals. In nonmetals, reactivity actually increases upwards. We're going to see this trend come back later on in this note when we talk about electronegativity. So this trend inverses upwards, and it's for the exact opposite reason. When you think about fluorine, that outside ring is really close to that positive center. So remember that it's that positive center that's attracting electrons. So since that outside ring is close to that positive center, the electrons are going to be even more attracted to fluorine because they're closer to that positive. Chlorine's a little bit bigger, so it's a little bit further away from the positive center, so it's not as attractive to incoming electron. Bromine is even bigger, so it's not as attractive. So essentially, the ability to attract an electron decreases, which means that it's going to be least reactive down here, and it's going to be most reactive right here. So this is an example of another periodic trend, where not only is there a trend between columns, but there's a trend within columns as well too. So now that we understand a little bit about what a trend is in a periodic table, let's take a look at the new trends that I'm going to be showing you today. So the new trends that I'm going to be showing you today are going to be electronegativity. We're going to talk about ionization energy, and we're also going to talk about something called net nuclear attraction. So in order to understand each trend, there's actually two things that we want to understand. So to understand each trend, we want to understand both shielding effect and net nuclear attraction. If you can understand these two things, you can actually understand any trend I'm going to throw at you today, and it's going to make memorization just much easier, right? We don't want you memorizing things in chemistry. I want you to actually understand what's happening so you don't have to worry about memorizing your notes. So let's first talk about shielding effect and what shielding effect is. Shielding effect is the number of electrons in a full shell between the nucleus and the valence electrons. So that sounds way more complicated than it needs to be. Essentially, let's say we've got our nucleus here. And remember that our nucleus is made up of a positive center. Shielding effect is essentially just a number of full shells that are in the way. So let's say we're dealing with something in the second row. These circles are real hard to draw in here. There we go. Let's say we're dealing with something in the second row of the periodic table. There's only one full shell between these valence electrons and that positive core. Remember, that positive core is that magnet that's actually holding those electrons in place. So this has less of a shielding effect because there's less stuff in the way. Now let's take a look at something that maybe is on the fourth shell of the periodic table. So something that's on the fourth shell or fourth row of the periodic table is going to have 4 shells. And here we have a greater shielding effect. So now that we're looking at something that's on the fourth row, we're actually 4 shells away. There's 1, 2, 3 shells in the way of these valence electrons and this positive core here. So here we would say shielding effect is greater for elements that are further down the periodic table than elements that are closer to the top of the periodic table. So let's talk a little bit about shielding effect in terms of how it affects trends in the periodic table now that we know what it is. So as we move from left to right across a period, shielding effect is constant. So all that we're going to do really quickly is we're just going to draw, let's just draw the valence electrons. No, let's actually draw the shells. So let's maybe start with lithium. So we know that lithium has 1 valence electron on the second shell. Then we're going to go ahead and we are going to move to beryllium next. And beryllium now has 2 valence electrons on that second shell. The next element is going to have 3 electrons on the second shell. And the next element, carbon, is going to have 4 electrons on that outer shell. So as you move from left to right, as you move down a row on the periodic table, shielding effect actually remains constant. So shielding effect, remember, is introducing a new shell. Here we haven't introduced any new shells. These electrons are being placed on the same shell. So shielding effect is constant from left to right. What this means is that shielding effect actually has no impact on trends going from left to right. So since shielding effect is the same, shielding effect is not going to impact anything going from left to right across the periodic table. Let's get my arrow back here. So let's look the other way now. Let's see what happens as we move down a group. So as we move down a group, the shielding effect is actually going to increase. So let's start with lithium again. We know that lithium has 1 valence electron on the second shell. Then if we move down to sodium, we know that sodium still has one valence electron, but this time it's on the third shell. And if we move down to potassium, potassium has one valence electron on that outside shell there. So as we actually go down, we're actually going to see the number of shells is going to increase. We're going to have 1 shell, 2 shells, 3 shells. So since we're increasing the number of shells, that means that there is going to be a greater shielding effect as you move down a column on the periodic table. So what this means is that as you move down, we're going to see an increase in shielding effect. There's going to be more full valence electron shells, so the atom is going to become larger. So as you move down a group, the atom is actually going to become larger. That means that the electrons are going to be further from the nucleus. So those outside electrons are going to be further away from the nucleus. They're going to be further away from the positive core. Since those outside electrons are further away from the nucleus, they're further away from the positive core, that means they're going to be less attracted, right? If they're further away, and also if there's more shells in the way shielding that positive charge, it means that those outside valence electrons are going to be less attracted to that center, to that positive core, to that nucleus. So the higher up we are on the periodic table, the less shielding effect, the more attracted our electrons are going to be. The lower we are on the periodic table, the more shielding that's happening, the less attracted our electrons are going to be. That takes a little while to stick. I understand that's complicated, but once you understand that, we can actually apply that to all of our trends that we're going to be talking about today. Let's talk about our next concept now, and our next concept is going to be net nuclear attraction. So net nuclear attraction, again, can take a little while to wrap our head around. Net nuclear attraction, the definition, we say it's calculated by taking the number of charge, taking the nuclear charge, Z, or the number of protons, and subtracting the shielding effect. So essentially, it's going to be taking the number of protons, taking it out of the situation, shielding effect, and seeing what's left. Net nuclear attraction is a relative measure of how the actual attraction between the nucleus and the valence electrons are in an atom. So we actually take out shielding effect. How will the attraction be impacted between those outside electrons and between that positive core? So this is kind of hard to think about. So why don't we take a look and think about that in terms of the periodic table? So again, net nuclear attraction is going to be measuring the attraction between the nucleus and the valence electrons. And let's talk about what happens when we move from left to right across a period. So we're going to, again, I'm just going to draw a little sketch here, but I'm also going to record the number of protons. So we're going to think about lithium again. And remember that lithium has one valence electron, but lithium also has 3 protons. Then we're going to take a look at our next element here, beryllium. Beryllium also only has 2 shells, but beryllium actually has 4 protons, right? It's got an atomic number of 4, so it's got 1 additional proton. Then we're going to think about boron. Boron is going to have 5 protons. Then we're going to think about carbon. And carbon is going to have 6 protons. So essentially, as I move from left to right, shielding effect isn't changing. We know that. But what is changing is the number of positives that are in my core. Remember, that positive core is acting like a magnet. So the more positives I have, the more attracted my outside electrons are going to be. So these outside electrons are all the exact same distance, technically, right? They're on the same shell, they're in the same energy level, but we're getting more and more and more of a stronger positive core. That means they're going to be more attracted. So what that means is as I go from left to right, as I go towards this direction, my net nuclear attraction is going to increase because I'm going to have more protons. All right, so let's look at this in the other direction. Sorry, before we move on, let's look at this in the other direction. Let's look at what happens when we actually move down. And when we actually move down, we're going to find that net nuclear attraction does not change. So if you're moving down an actual column, then you're going to find net nuclear attraction is going to stay the same. If you're moving from left to right, that means that net nuclear attraction is going to go ahead and it's going to increase. So what we've done down here is we've summarized that in a nice little chart. So trends that are going across a period, so going from left to right, are due to net nuclear attraction. How do we know that? Well, shielding effect is staying the same. Net nuclear attraction is changing. Trends that are going down are due to shielding effect. Well, how do we know that? Well, net nuclear attraction is the same, but shielding effect is changing. Shielding effect is increasing. I have more of those full shells. So now that we understand the basis of this, let's take a look at some of our trends. And for every single trend, we're going to think about how does shielding effect and how does net nuclear attraction come into play. So our first trend that we're going to talk about is atomic radius. Just a reminder, we've done a little bit of chemistry review already, but just a reminder that atoms have an equal number of positives and negatives. So atoms don't carry a charge. We're going to define atomic radius as half the distance between nuclei of adjacent atoms. So essentially an atomic radius, I've got my atom here. Let's say we've got my nucleus. And my atomic radius is essentially going to be this distance here. So it's a measure of essentially how big an atom is going to be. So it's going to give us an indication of an atom size. All right, so we want to think about this trend in terms of shielding effect and in terms of net nuclear attraction. So first of all, the size of an atom decreases as we go from left to right across a period. So as we go from left to right across a period, so as we go in this direction, the size of my atom is actually going to decrease. So I'm going to be the biggest here, and then I'm going to get smaller, and I'm going to get smaller, and I'm going to get smaller. Now remember, as I go from left to right, I'm not adding new shells. So I'm not adding new energy levels. So I'm not getting smaller because there's less shells. So what's happening? Well, it must be due to net nuclear attraction. We know it's due to net nuclear attraction because any trends going from left to right are due to net nuclear attraction. So let's kind of logic this out in our head. We know that when we talk about the far left, here, this is the least net nuclear attraction. So that means that those outside electrons have the least pull. So they're going to be biggest. Then I know if I take a step in this direction, I've got more net nuclear attraction. I've got a stronger positive core in the middle. So what's going to happen is these electrons are going to float just slightly closer to that positive core. That's going to make my overall atom smaller. It's going to be a really slight difference, but it's still going to be a difference. As I take a step over here, I've got even more net nuclear attraction. So these are going to pull in a little bit more. Take a step here, these are going to pull in a little bit more. And eventually I'm going to see my atom is the biggest on the left and the smallest on the right. It's the smallest on the right because it has the most positive core. It's got the strongest magnet pulling it towards the center. So our trend going from left to right is due to net nuclear attraction. Let's look at what happens then when we go down. So we know that as we go down, shielding effect is going to increase. So I go from having one shell in the way to having two shells in the way to having three shells in the way. I'm going to stop drawing circles because they're getting messier, right? There we go. So not only am I adding more energy levels, but those outside electrons are getting more loosely associated to that positive core. So these outside electrons here have the least amount of attraction to this positive core, so they're actually floating the furthest away. So as I go down a column, I'm actually going to see my atoms are going to get bigger and bigger and bigger because those outside electrons are going to have the least amount of attraction to that positive core. So we can now summarize atomic radius in terms of left to right. We can now summarize atomic radius in terms of up to down. So why don't we go ahead and take a look at an actual diagram and see if we are correct. As we move from left to right, you can see this visual representation, and my atoms are smallest over here, and my atoms are largest over here. So as I go left to right down a row, I see that my smallest atoms are on the right, my largest atoms are on the left. This is consistent with what we predicted. As I go from top to bottom, we can see that my largest atom is at the bottom and my smallest atom is at the top. So if I was looking for the largest atom on the periodic table, I would want to look at the bottom of a row, and I would actually want to look at I'd want to look at the bottom of a column, and I would want to look at the start of a row. So I would want to go ahead and look at cesium, and in fact, cesium actually has our biggest radius on this diagram. Opposite is true for the smallest atom. I would want to look at the top of a column, and I would want to look at the end of a row, and we're going to find that our smallest atom is helium, and that's true on this diagram. Helium is our smallest atom. So we can actually see our periodic trend of smallest from here and largest going all the way down here. So now what that means is, now that you understand periodic trends, or at least the periodic trend of atomic radius, it means that you don't have to look up this information. So if I asked you what's larger, manganese or iron, you don't actually have to look up these values. You can say, well, manganese is larger because it's closer to the left. If I ask you what's larger, calcium or strontium, you would say, well, strontium's further down a column, so strontium's going to be larger, calcium is going to be smaller. So if you understand these trends, it actually means you don't spend as much time looking up values as you would if you don't understand these trends. Let's look at another trend, and our next trend is going to be ionic radii. So just a reminder that an ion is a charged atom. So an ion has an unequal number of positives and negatives. So I've either gained negatives or I've lost negatives. Since it could either be a positive ion or a negative ion, we're going to kind of have to look at two different trends here. So a reminder that the addition or removal of an electron from an atom is going to result in an ion. Let's take a look at positive ions first. Positive ions are always going to be smaller. So let's think about lithium again. And if we're thinking about lithium, in terms of an ion, is going to lose its outside valence electron. Lithium's going to lose its outside shell. So naturally, the lithium ion is going to be smaller than the lithium atom. It's going to be smaller because it lost its outside shell. If it's losing an outside shell, then we've got a smaller ion than we do atom. The other reason is because now we have our positives outweighing our negatives. So we now have 3 positives in my core, and we only have 2 negatives, 2 electrons. So those positives have a really great hold on those electrons. So it's actually going to go ahead, net nuclear attraction has been increased, and it's actually going to pull those electrons even closer to it. So that shell that houses the electrons, you're actually going to see that shell is actually going to be even closer to the nucleus because there's now more positives than there are negatives, and that means that the net nuclear attraction has been increased. Now that we understand positive ions, let's take a look at negative ions. Negative ions are going to be the opposite. So let's take a look at, let's say, fluorine. So for fluorine, I'm actually going to go ahead and I'm going to gain an electron. So I've got a I've got a full first shell, and I'm going to draw myself a second shell. And remember that fluorine is now going to go ahead and it's going to gain an electron. So it had 7 valence electrons. It's now going to gain an electron. It's now going to have 8 electrons. So fluorine actually has gained an electron. It now has 10 negatives. It hasn't gained a proton, so it still only has 9 positives. Now what's happening is there's more negatives than positives. Since there's more negatives than positives, net nuclear attraction has decreased, and those negatives are floating slightly further away than they were before. So if I had had equal numbers of negatives and positive, it would be a pretty tight hold. Since I have an extra negative, it's floating slightly further away, it's slightly larger. So what this means is that negative ions are going to be larger than their neutral atom. It's because they're gaining an electron. Since we're gaining an electron, we're going to have less net nuclear attraction, and that outside radius is going to be further away. Let's take a look at another trend. And another trend here is called ionization energy. So let's start by defining what ionization energy is. Ionization energy is the amount of energy required to remove an electron from an atom. So I'm, again, a visual person, so I like to picture myself kind of as a giant and with a giant atom and actually plucking an electron off. So how hard I have to pull on that outside electron, that would be like my ionization energy. If I have to pull really hard, it's got a really high ionization energy. It means that electron is really stuck on there. If I don't have to pull as hard, it means that it's got a low ionization energy. That electron isn't attached as well. It's not as strongly attached. We have a couple of different types of ionization energy. The first ionization energy is the amount of energy required to remove the outermost electron. So the first ionization energy is the amount of energy if I want to pluck off just one electron. Second ionization energy is the amount of energy required to remove the second outermost electron. So let's say I've removed one electron and I want to go ahead and now remove that second electron. That's going to be my second ionization energy. My third ionization energy is going to be if I want to remove a third electron, and so on and so forth. So the outermost electron is the easiest electron to remove. Removal of subsequent electrons require more energy. So what that means is that the smallest ionization energy is going to be my first ionization energy. My first electron is my easiest to remove. The reason why is because my first electron, positives and negatives are equal. So let's talk about carbon. In order to remove my first electron from carbon, I'm going to have 6 positives. I'm going to have 6 negatives. Forces are approximately equal, so it's going to be easiest to remove that first electron. If I want now to remove a second electron, second ionization energy, I now have 6 positives, but I only have 5 negatives. So these positives have an even tighter hold on electrons. So removing that second electron is going to be even harder than removing that first electron. If I want to remove a third electron, same idea. I still have 6 positives, but now I only have 4 negatives. They've got an even tighter hold on that outside electron. It's going to be even harder for me to remove that outside electron. So first ionization energy is the smallest. Second ionization energy is the second smallest. Third ionization is the third smallest, and so on and so forth. All right, now that we understand the difference between first, second, and third ionization energy, let's look at ionization energy within the periodic table. So let's think about what happens when we move from left to right across a period. So again, moving from left to right across a period, this is going to be related to net nuclear attraction. So let's think about what we know about net nuclear attraction. We know that here we have the least attraction to electrons, and here we have the strongest attraction to electrons. Remember, I'm talking about the effort that's required to pull off an electron. So it's going to be much easier to pull off electrons here than it is here. Here I have less of a hold. I only have 3 protons holding on to my electrons, whereas here I have 7 or 8 protons holding on to my electrons. It's going to be much harder to pull electrons off down here. So on this side, we say that I have the smallest holds. Here I have the largest holds. So what this means is that ionization energy is going to increase as you move from left to right across a period. So it's pretty easy to remove electrons here. It's got a small ionization energy. It's more challenging to remove electrons here. I've got a larger ionization energy. So ionization energy is large on the right and it's small on the left. Now that we understand the trend of going from left to right, we also want to look at the trend of going down a column. And we know that going down a column is due to shielding effect. So let's think about what happens as I go down a column. As I go down a column, I'm going to have more attraction up here, and I'm going to have less attraction down here. I have more attraction up here because I have a smaller atom, I have less of a shielding effect. I have less attraction down here because I have more of a shielding effect. So that means it's going to be easier to remove electrons down here. That means it's going to be harder to remove electrons down here. So that means that ionization energy down here should be smaller. Ionization energy up here should be larger. So ionization energy decreases as you move down the group. It's because of shielding. So inner shells that are filled shield the outermost shells from the positive charge, making the outer electrons easier to remove. So down here we have a smaller ionization energy because it's easier to remove those electrons, and that is due to shielding. So again, we've got a trend going from left to right. We've got a trend going from up to down. So let's take a look at what this looks like on our periodic table. If we want to find the highest ionization energy within a row, we want to look at the very end of the row. It is the hardest to remove electrons here. It is the easiest to remove electrons here. So ionization energy is going to be highest here. If we were looking down a column, again, we want to look at the top of a column. That's because electrons are hardest to remove up here and electrons are easiest to remove down here. So if we were looking at increasing ionization energy goes this way and it goes this way. So the element with the highest ionization energy would be helium, and the element with the lowest ionization energy would be francium down here. And when you actually look at the values, that is true. So we actually do have the trends in the periodic table follow what we would expect. Let's take a look at another trend. We actually have two more we want to look at. This trend is called electron affinity. So here with electron affinity, what's really nice about these trends, you're going to see a lot of overlap. So you're going to see electron affinity has almost the exact same trend as ionization energy. It's really just a different definition. So electron affinity is the amount of energy released when an electron is added to an element. Okay, so what we're going to see is this is almost the exact same number as ionization energy, just with a different sign. So let's say we're talking about lithium, and let's say we're talking about removing that outermost electron. So if we want to remove that outermost electron, it's going to require energy. Let's say it requires, I'm just going to say 30 joules. Totally made that number up. I don't actually know how much it requires off the top of my head. I'd have to look that up. So let's say it takes 30 joules of energy for me to actually pull off that electron. When I go to add that electron back on, that energy is going to be released. It's going to go in the opposite direction. So if pulling an electron off takes energy, that means putting an electron back on is going to release energy. It's actually going to release the exact same amount of energy as required to pull it off. In order to show that this energy is being released, we just go ahead and we throw a negative sign in front of there. We're going to cover that much more in grade 12 chemistry, but you're going to cover that in physics this year. So if you've already taken physics, you've already seen the whole idea of energy going from one direction to another. So essentially with electron affinity is going to be the exact same trend as ionization energy because it's the same number, essentially with a negative in it. So the amount of energy released when an electron is added to an element is our electron affinity. The higher an element's electron affinity, the greater the attraction for an electron. So if something's got a really high electron affinity, that means it's going to release a lot of energy when I add it back on. That means it took a lot of energy to pull it back off. So a high electron affinity means that it's got a really high attraction for electrons. So let's take a look at what happens with this trend left to right. As you would expect, it's got the exact same trend as ionization energy. When I go down here on the right-hand side, I've got a greater attraction for electrons. Since I've got a greater attraction for electrons, I've got a greater electron affinity due to net nuclear attraction. So electron affinity increases as you move from left to right. So I'm going to see my highest electron affinity on my right-hand side. We're now going to look at our trend going down a column, and as you would expect, going down a column, it's the same as ionization energy. So again, as I move down a column, as I go down a group, I've got less attraction at the bottom, I've got more attraction at the top. That means since I've got more attraction at the top, I'm going to have a greater electron affinity up here, and I'm going to have a smaller electron affinity down here. Why is that? Shielding effect. Down here, I have way less, down here I have way more shells in the way of those outside valence electrons. Since I have more shells in the way, I've got a looser attraction. Up here, there's barely any shells in the way. Since there's barely any shells in the way, I have a very strong attraction between my outside electrons and my positive core. So again, let's take a look at a diagram and let's see how this is going to look on the periodic table. So going from left to right, electron affinity is going to increase. Going up, electron affinity is going to increase. Well, this is the exact same trend as ionization energy. So helium is going to have the highest electron affinity, and francium is going to have the lowest electron affinity down here. So again, if you have a really good basis of understanding of net nuclear attraction and shielding effect, you can see that understanding these trends is not as hard. They end up actually being the same thing kind of over and over and over again. If you don't understand electron affinity, if you don't understand shielding effect, or if you don't understand net nuclear attraction, it's much harder to understand these trends. Last thing we want to look at here is going to be electronegativity. Now, I've kind of saved the best for last. I hope you just didn't pause the video and say, hey, I can figure this out, because electronegativity is actually going to be the most important trend. So I want to end with it because it's going to be the trend that we're actually going to talk about the most this year. When we talk about Lewis diagrams and compounds, I'm going to always come back to electronegativity. And when I talk about polarity, I'm going to come back to electronegativity. So this is the most important trend. So again, if you can understand how the periodic table is set up based on electronegativity, you have way less time actually looking up values if you can just kind of understand how the periodic table is organized. So the definition of electronegativity is the ability of an atom to attract an electron away from another atom. So it's the ability to actually steal an electron. If an atom has a really high attraction for electrons, it's going to have a high electronegativity. It's like a guy winning a tug of war, right? So if you have a really, really strong guy, he's going to win your tug of war. He's actually going to steal the rope from someone else. If you have a less strong guy, or let's say you have a strong female, less strong female, then your less strong female is going to lose your tug of war to your stronger female because she isn't as strong. So electronegativity, the higher your electronegativity, the stronger attraction you have for electrons. The lower your electronegativity, the less attraction you have for electrons. Elements with higher electronegativity have a strong tendency to gain electrons. So if you have a high electronegativity, you're going to gain electrons. You're going to steal other people's electrons. If you have a low electronegativity, you're going to get your electrons stolen. You're going to lose electrons. So let's take a look at the trend going from left to right. So the trend going from left to right, again, the attraction for electrons is higher here. We have a net nuclear attraction higher on the right. We have a lower net nuclear attraction on the left. So you would expect that electronegativity would be higher on the right. That means that elements that are on the right-hand side of the table are going to be much more likely to gain electrons. Well, think about what you know about ions on the periodic table. All the ions on the periodic table on the right-hand side are all negative. Negative ions means that they're gaining electrons. So it actually matches the trend that you learned in grade 9, right? So on the right-hand side of the periodic table, we're gaining electrons. That's because we have a higher electronegativity. Why do we have a higher electronegativity? That's due to net nuclear attraction. Finally, let's take a look at our trend going down a group. So if we think about our trend going down a group, we know we have less attraction at the bottom. We know that we have more attraction at the top. So that means that electronegativity is going to be higher at the top. You're going to see more of a tendency to steal electrons at the top than you are at the bottom. At the bottom, there's less of a hold on those valence electrons. There's more shells in the way, shielding that positive core. Since we have a loose hold on those outside valence electrons, it's going to be very easy to lose them. We're going to have a low electronegativity. So as we go down a column on the periodic table, as we go down a group on the periodic table, we're going to see that our electronegativity decreases. So what does this look like in terms of a periodic table? It looks like this, where our highest electronegativities are here and here. So our most electronegative atoms should be helium, right? Not necessarily true. Why is this not true? Well, let's think about this logically. Electronegativity is the ability to want to gain an electron. Does helium want to gain an electron? No, it's full. It doesn't want an electron. It doesn't care. So neon, helium, argon, we actually don't really assign electronegativities to the noble gases because they don't want electrons. So electronegativity doesn't necessarily apply to them. What you want to look at is you want to start here with the halogens. So our highest electronegativity is actually fluorine in this case. It really, really, really wants to gain an electron. It's small, so that outer shell is really close to that positive core, and it's almost full. It only needs one more. So fluorine is the most electronegative atom, whereas francium down here is going to be the least electronegative atom. So understanding these trends is going to be really important when we look at forming compounds, because when we form compounds in a day or two, we're going to be looking at gaining or losing electrons. So if you can understand the trend in electronegativity, you can say, yeah, lithium has way less of an electronegativity than fluorine. So lithium is probably going to lose the electron. Fluorine is probably going to gain the electron. It's going to help you with important decisions as well, too, between elements that are maybe closer, right? Aluminum and chlorine. You can see here, aluminum is probably going to lose an electron to chlorine because aluminum is further to the left than chlorine is to the right. So those are our trends in the periodic table. Now I'm going to give you a graphing activity. So I want you to actually graph these trends. What you are going to find is chemistry is awesome and there's always exceptions to the trends, right? So I'm going to actually have you graph a couple of these trends, look at them. I'm going to see you, how you can match it to the periodic table and see if there's any anomalies or any exceptions to the rules and see if you can explain them. So good luck with periodic trends. Good luck with your graphing activity. If you have any questions, let me know. Have a great day. See you later.